Welcome to session 1 of the Generalized Linear Models lecture. So in general, generalized linear models are really just a way of dealing with conditional distributions in which the parameters are expressed as functions of linear combinations of the conditioning variables. They take on a special characteristic because when they are of a certain form, they have some kind of computationally useful attributes. So to start, we'll look at what kind of began the GLM trend years ago, and that is the exponential family of distributions. And the exponential family of distributions contain basically all the distributions that can be written as the exponentiation of a number of functions. One is a vector of functions of the parameters of the distribution. Another is functions of the random variable y. And then we have another which is, again, a function of the parameters. And then finally another that's a function of the data again. The first two are multiplied by each other in a vector multiplication sense. And then the last two kind of stand alone additively in the exponent. So what we can see is then if we think of beta as a k by 1 vector of functions, a is then a k by 1 vector of functions of y, c is a function of theta, and d is then just a function of y. And it's key to say that d is not a function of theta. For example, let's consider the gamma distribution. So the gamma distribution CDF is typically written in this form, and that is beta. It has two parameters, beta and alpha, and this PDF is written as beta to the alpha times this gamma function evaluated at alpha, and this is a type of a mathematical function here, this capital gamma, multiplied by y to the alpha minus 1, e to the negative beta y. But we can re-express this as e to the log of this, if you want to think of it. If you take then the log of that, then e to the log of that is going to get back this distribution. So if we log this upper part, we will get a negative by plus alpha minus 1 times log y plus an alpha log beta minus a log gamma alpha. So here we can set the functions that we had above, is b, a, c, and d, accordingly. We can say that b is negative beta and alpha, and that is going to pick out essentially what we would have this term here and this one here multiplied by the log alpha, it'll turn out. So a is y and log alpha, and c is alpha log beta minus log alpha. It's this part here. And then the final dy is just log y, and that came from this component here. So we broke this one up into two parts. The alpha log y part of this comes from the multiplication of these two. So gamma is a member of the exponential family. Now, just so that we can proceed further a little bit, remember, and we've gone over this before, that since the integral of a density is equal to 1, and assuming that mathematically we can switch the derivative with the integral, then we can say that the derivative of the integral is equal to 0 because it's a constant, right? Derivative of 1 is constant. Therefore, the integral of the derivatives is equal to 0. Okay, and then the second derivative is also equal to 0, and therefore the integral of the second derivative is also equal to 0. So now let's consider then that the derivative of the density with respect to the vector of parameters theta, and use the fact that this integral of the derivative of the density is equal to 0, and we can solve for the expected value of y. So we take the derivative from above and it comes down to beta, the first derivative of the b function with respect to thetas, times the ay function plus the first derivative of the c function with respect to thetas, times the density. We can set this equal to 0. Notice we said it was equal to 0, so we can set this equal to 0. That's something to notice. So now if we take the integral of this function, which is our integral, we come up with the first derivative function times the expected values of ay plus the first derivatives of c. We set that equal to 0, and we solve, and we find out that the expected value of a is equal to the function of, as expressed here, which is essentially the b times the b1 transposed inverse times the b1 times the c1, negative in front of all of that. If you follow through on the dimensions, you come down to a k plus 1 vector out of this, which is exactly what we would expect of this, because a was a k plus, k by 1, and because a was a k by 1, this matches as it should. We do the same thing with the second derivatives. So the second derivatives, if you look very closely and do the derivatives carefully, you will come up with this particular term, and that is a function now, the second derivative matrix associated with the b function, capital B function, times ay times the second derivative of c times the density. And then we have the first derivative times a plus c, its first derivative, times the same quantity transposed times the density, which, as we move it around a bit, we get this expression here. This is equal to 0, as we had mentioned above about the second derivatives. And we can integrate this, and we can integrate, not that, but integrate what we have above, and we get the second derivatives times the expected value of a plus c times the b first derivative transposed expected value of a transposed times b, 2 times b times the expected value of a times the c first derivatives of c, plus c transpose. And we can solve for the expected value of a transpose. And this is a huge mess. The reason it is because actually this matrix is really a multidimensional array of derivatives, and it is in fact a k by p array. You need to keep track then of a multidimensional array of factors, and we can do that in there. It's just a higher order way of dealing with matrix multiplication. It's kind of array multiplication. But alternatively, you can also use vec operators, which basically means that you vectorize the matrix and you reduce it back down to simple 2 dimensions. But you just got to be careful how you do it. And this is beyond the scope of this course, so I won't be concerned about getting into the details on how actually to solve this. The point is that just like we solve for the mean, we can solve for this matrix, which would give us the variances. Where we're going to head is we're going to essentially consider one parameter models fixing all other parameters. So we're going to say all the parameters are fixed. Think of it as fixed to a constant. We're going to just think of what happens in terms of one parameter. So in this case, although no, I'm not going to, but nonetheless, we will typically do that. But here's an example of a gamma distribution, and it's e to the, what I'll call g now, is that whole set of terms that goes in the exponentiated form, and here's what it is there. It is a negative beta y plus an alpha log y minus log y and alpha log beta minus log gamma alpha. And what does that give us? Well, if you look closely, our AY is y and log y. Right? So it's going to pick up this y here, and it's going to pick up this log y. Our B vector is the negative beta and the alpha. Our C is this term here. And then we have our function of negative log y. If we take the derivatives of B with respect to alpha and beta, we get a matrix of negative 1, 0, 0, 1. And the derivative of C, we get alpha over beta, log beta, psi alpha. And don't worry, that's just another type of mathematical function. And then we take our derivative again of dc with respect to beta. We get alpha over beta squared, 1 over beta. And if we take the derivative of dc again with alpha, we get this 1 over alpha and this negative psi 1 in alpha. Again, it's a mathematical function. You could look it up. It'll calculate to a certain value. And so overall, we get this matrix. Now, the expected value of y, of A, in this case, is this term, as we had written before, the negative. Now I call it the derivative of beta transpose, the derivative inverse, the derivative times derivative of C, and it simplifies to this term here, which right here simplifies this term, alpha over beta and this component here. Obviously, if we were really concerned, our main concern is the first one, typically, because we're looking at a gamma distribution associated with the distribution of y. The log y is a separate term, but if you wanted it, you've got those terms here as well. So what about the variance? Well, first, the second derivative, notice, is because is 0, again, as we said, because this is a constant matrix. And here again is that big long equation that I said the second derivative would work out to be. And if we look at it carefully and do the algebra, here is our matrix for which that is going to be the variance for the y term. So as a numeric example, if we let alpha equal to 2 and beta equal to 1 over 4, then our mean is 8 for the y and 1.809 for the log y. And we have our log 1 alpha is equal to this term if you were to plug it into a computer, pi squared over 6 minus 1. I'm using MathCAD here and I was having trouble doing it directly, so instead I calculate it and then stick it in separately into this matrix. And now we've got our alpha over beta 2, 1 over alpha, and we end up with a variance of 32. We end up with a variance of 0.64 for the log y, covariance of that. The main ones of interest, of course, is for y, so we've got our 32, and up here, the main one of interest was our 8. So if we just let AY be a 1 by 1, and not two terms, and theta is a scalar, then our expected value of AY just comes down to a negative first derivative of the C function divided by the first derivative of the B function. And the variance will distill down into, if you work on it, do the algebra, you will get the second derivative of B divided by the first derivative of B times the expected value of AY, which was written up here, minus the second derivative of C2 and the first derivative of B squared. Noting that this is a function of the mean, so the whole variance is, in fact, a function of the mean. This is again assuming beta 2 is not equal to 0. If that's equal to 0, then obviously that won't be true. Or it'll be a function of the mean, but it'll be a function of the mean in a trivial way. Right? So what we get here is our variance expressed as a function of the mean. And this is key because when we move into stata, this is going to be part of what we have to determine is what kind of a function of the mean are we going to consider our variance to have. One more example here. Let's look at the normal distribution. Here we're going to think about the mean. The variance we're going to consider is known as a fixed value. So here's our classic density that we're all familiar with a normal. But if we take e to the log of that, what we end up with is a y times mu over theta. So here is our ay. Notice now it is just simply y. There's not a vector. And our b function is mu divided by sigma squared. Our d is going to be this term here with the y squared divided by 2 sigma squared in it. And c is the remainder, which is just a bunch of terms of the parameters. Our expected value of y is the derivatives divided by each other minus. So we have our minus if you were to go up here and take the derivatives of each of these. Right? You would get, so here is the derivative of c. We want to take the derivative of c and we want to take the derivative of b. And what we get is negative mu sigma squared divided by 1 over sigma squared, and take the negative of that quantity and you do a little bit of algebra, you find out that it is equal to mu, which is not surprising. For the normal distribution, the expected value of y is equal to the parameter, which I happen to label mu, and b2 is equal to 0, which means, as I said above, that the variance will not be a function of the mean in any meaningful way, or it's trivially a function of the mean, just as a constant could be considered, and it is negative the second derivative of c divided by the first derivative of b squared. Plug those terms in and you get sigma squared. So this is not, shocking. It's what we would be expecting since we already understand the normal distribution. But that's comforting to know. So, in summary, if ay is equal to just simply y, then we can simply express the exponential family in this form here. Okay. Which I guess would be better said, those distributions for which this is the case, they are part of the exponential family, and we can express it this way, where the density is exponentiated. It's a function of y times theta minus some function b theta, divided by some parameter alpha that's a function of parameters phi, and we'll see what that comes out to be later, and then some function of c and these phi parameters. So this ends the first session of generalized linear models, and we will continue on looking at the simple and then get a little more complex again in the following lectures.